Today, we're going to pull back the curtain on one of the most incredible, invisible engines of the internet, the web crawler. These are the digital explorers out there mapping the massive, constantly changing World Wide Web. Honestly, they're the reason search engines can even exist.
But have you ever really stopped to think about it? How in the world does Google or any search engine find a brand new article you just published, like moments after you hit go live? The answer isn't magic. It's just a really, really brilliant piece of engineering that's built to handle unbelievable scale. And at the very heart of that system is the web crawler, or as it's sometimes called, a spider. You know, the best way to think about it is like a super fast, tireless digital librarian. It starts with a list of pages, reads them, and then follows every single link it finds to discover new pages, just endlessly expanding its catalog of the web. Okay, so let's break that down. This visual really lays out the core idea. The crawler gets a few starting points. We call them seed URLs. It fetches a page, pulls out all the hyperlinks on it, and then adds all those new links to its giant to-do list. Then it just repeats the process, visiting those new pages, finding more links, and just branching out, mapping the web link by link by link. Now, that sounds pretty straightforward when you're talking about a few dozen pages, right? But what happens when your job is to crawl the entire internet? This is where the real fun begins. We're not just designing for a few pages, we are designing for billions.
So let's get real and put some numbers to this challenge. Our main functional requirement is just raw scale. The goal, collect 1 billion web pages every single month. That is an absolutely staggering amount of data to find, download, and process.
So, what does a billion pages a month actually look like in terms of speed? Well, if you do the math, it boils down to needing to download around 400 pages every single second. 24/7, that number right there defines our required throughput. It's got to be fast.
Okay, and where are we going to put all this data? Let's say the average web page is about 500 kilobytes. If we need to store 5 years' worth of this crawl data, we are looking at 30 petabytes of storage. That is a massive number, and this kind of estimation directly impacts what kind of database and storage systems we're going to choose.
So, these huge numbers lead us straight to our core design goals, our non-functional requirements. First, the system has to be scalable to even handle this fire hose of data. It's got to be robust because, trust me, the web is a messy, unpredictable place full of broken HTML and slow servers. And this is a big one. It must be polite. We can't just hammer websites with requests. That's a great way to get blocked. And finally, it has to be extensible because the web is always changing and we need to be ready for what's next. All right, with those goals locked in, how do we actually build this beast? Let's zoom out and look at the high-level system design, the blueprint for our billion-page crawler.
I love this diagram because it shows the entire life cycle of a URL. So look at step 1. We start with our seed URLs, and they get fed into this thing called the URL frontier. Think of the frontier as our smart to-do list. It hands URLs over to the HTML downloader. After the page is downloaded and checked for duplicates, the link extractor at step 7 does its job finding all the new URLs. Those get filtered, checked against the list of URLs we've already seen, and then, at step 11, the new, unique URLs get sent right back to where they started, the URL frontier, and the whole cycle begins again.
That entire workflow we just saw, it really all hinges on that one component. So let's do a deep dive into what I'd call the brains of the whole operation, the URL frontier. This thing is so much more than a simple list. It's an incredibly sophisticated system for deciding what to crawl next and when.
Okay, so if you remember your computer science basics, there are 2 classic ways to explore a network like the web: depth first and breadth first. Now, DFS is a terrible idea for web crawling. You could literally get stuck in an infinite rabbit hole of links on one site. So crawlers use breadth first search, or BFS, exploring the web level by level. But using a simple first in, first out queue for this has a massive, massive flaw. And this slide illustrates that flaw perfectly. Let's say our crawler finds a huge site, like Wikipedia. A simple queue is suddenly going to be flooded with thousands of links, all pointing to wikipedia.com. And if our downloaders just start working through that queue, boom, we're slamming Wikipedia's servers with hundreds of requests a second. That is incredibly impolite, and it's a surefire way to get our crawler's IP address banned. This really gets us to a fundamental rule of web crawling. You have to be a good internet citizen. Politeness isn't just a nice-to-have feature, it's an absolutely critical requirement. Without it, the crawler just can't do its job without disrupting the very websites it's trying to index. So the million-dollar question is, how do we solve this? Well, the URL frontier uses this really ingenious two-part strategy. First, it uses what are called front queues to prioritize some URLs over others. For example, a major news homepage is probably more important to crawl frequently than some random forum post. Then, and this is the magic part, it uses back queues to group all the URLs by their host, which is the key to solving that politeness problem.
And here is the complete design that ties it all together. It's beautiful, really. URLs come in and are first put into those priority-based front queues. A selector then picks a high-priority URL and sends it to a router. That router looks at the domain, say apple.com, and makes sure it goes into one specific back queue just for apple.com. The same thing happens for nike.com, and so on. Then each downloader worker is mapped to a single back queue. This guarantees we only hit one website at a time, very politely. It's just an incredibly elegant solution to a really tricky problem.
Okay, so we've got the core logic sorted. But now we have to talk about making this entire system tough enough to run 24/7 without breaking and flexible enough to adapt to whatever the future throws at it. You know, when you're building something at this scale, you have to assume things will fail. It's not a question of if, but when. So we use things like consistent hashing to spread the load of URLs evenly across our many downloaders. We're constantly saving the state of the crawl, so if there's a crash, we don't have to start over from square one. And of course, you need rock-solid exception handling and data validation to make sure one bad web page doesn't bring down the whole system.
And what about the future? The web isn't just text and HTML anymore, right? So to make the system extensible, you build it with a modular design. This diagram shows it perfectly. If, down the road, we decide we also want to start indexing images, we can just build and plug in a new PNG downloader module. We don't have to go back and re-architect the entire system from scratch. So when you boil it all down, what's the big takeaway here? I think it's that designing a web crawler is a masterclass in trade-offs. It's this constant, delicate balancing act between four competing forces. The need for incredible speed, the demands of massive scale, the absolute requirement of politeness, and the complex logic of priority. And that kind of leaves us with one final big question. We've just designed a crawler that's perfect for the web of today. But the web is always evolving. We're moving beyond static pages into a world of dynamic apps, APIs, and even AI-generated content. So how will the crawlers of tomorrow have to adapt their fundamental design to keep mapping our ever-changing digital universe?